So now we're going to talk about small signal modeling. And I will say that small signal modeling is one of those questions and topics that is probably known to many electrical engineers and probably misknown by a lot as well. Um, Small signal modeling is really a way of talking about when I have small signals, or I know I have a system that's primarily linear, to start to actually do analysis in a linear domain. And because it's linear, I can then create linear circuit elements to do this. And this is really useful because we can really bring all the tools that we know about linear circuit design and linear concepts and linear analysis into the question. But most people tend to actually have a huge number of misunderstandings of where this comes from. That could be a whole lecture unto itself. But the simple comment to understand is that when you do small signal model, you're doing two things first. And there have to be two things that you always have to be thinking about. One, you always have to remember that you are removing the DC out of the system. And I can't tell you the number of times I've seen a student look at a problem and then try to immediately simulate or build it and assume that the DC is zero and nothing works and wonders, my gosh, something's completely wrong. The answer is yeah, because you forgot your biasing terms. I guess it's a fair comment to say that we all have to be biased to work well, so that's probably a good thing to learn both in circuits and probably in life too. The second thing is, at that point, then you're linearizing the elements. In theory, I could do either step technically, independently of each other, but I need both steps, and the linearization then is important and creates these particular elements that we're working with. So that's really important to understand where those are coming from. Now, if I'm dealing with an NFET or a PFET device, these are my devices here, and I'm going to use these definitions, B1, B2, and B3. Basically, they're going to be gate, source, and drain. Obviously, remember the source and the drain are defined differently, given because I've actually told you the current is going in a certain direction. So, but if I use these definitions, and remember I would be using a device, say it was in subthreshold, and I kept the subthreshold equation here for you, because this is very useful to always remember kind of where this comes from. And we're always going to be, kind of going back to that. Now there's a whole set of expressions for above threshold, and those are actually in other lectures as well. Now, if I take this, what I'm going to be asking is, what is going to be the small signal changes in this term in terms of source current, right? Basically the current going from source to drain. And I'm going to look at that partial change if I made it, and there's only one current, so that's all we really have to worry about here, which is kind of nice, as a function of change in the gate voltage, as a function of change in the source voltage, as a function of change in the drain voltage. Those three things are the things I care about. And I would compute those derivatives. Now the nice thing about exponentials is the derivative of what's derivative in exponential is really just an exponential, and then other things come out of it. So it's a very useful and nice formulation for many of these systems. Also remember, if you've looked at a couple of circuits already doing large signal and subthreshold, we already know that the solutions are basically linear. So not a bad thing to do small signal model, but don't forget that it really, you really can do some large signal solutions. Above threshold sometimes is the only way to get a reasonable solution in a reasonable amount of time. But what's interesting is if I take this definition of source current, it's got three components. The linear component due to the change in the source voltage, or the gate voltage, the linear component due to the change in the source voltage, and the linear component due to the change in the drain voltage. I will get all three of those terms. And effectively, this gives me voltage-controlled current sources that represent that sort of change in voltage, the differential current, the additive current, added to the bias current, right? We remove all the biasing details. That I'm going to get in the source gate voltage. I'm going to get one on the source voltage and one on the drain voltage. So these are three constants, GM, GS, and R0, or sometimes thought of as an output resistance in some cases. Notice that each of these terminals has a term unto itself. And that's not surprising when you take a look at what's in the exponential. I see kappa in front of the gate voltage, so I would expect it'll have one term. I see just a -1 in front of the source voltage. I expect it's going to have its own term. And third, I have I have sigma in front of the drain voltage. Now, at first, you might think this is a lot of voltage current sources, and a lot of students actually get very nervous about, oh my gosh, that was the part of the circuits that were hard. I'm like, it's actually not that bad. It's actually in some ways easier because now it's dependent on a single voltage. And what you'll find is many times, for example, if I was doing a common source amplifier, this just whole current source goes away and I just have just these two to do my analysis. If it was a common gate, that would mean that this would be at a DC potential and this one would go away, and so forth. And we'll find a lot of cases where the analysis is much faster, much more appropriate this way. So this is going to be the modeling we'll use. It really is actually quite elegant and quite simple to use when you do sort of linear circuits. And the thing I like about doing small signal models is it allows you to actually draw circuits and actually use your sort of graphical intuition, not just writing analytic equations. And many times you can actually reduce things to a very simple sort of graphical form. So if you look at this, you actually will get three terms. And for the GM, GS, and R0 at subthreshold, you get kappa I over UT, again, something that comes out of the exponential, just taking the derivative of the exponential. For GS is I over UT, so these look very, very similar. Okay, not too much surprise there. And the output is, the R out is really going to be UT over sigma I, or if you'd prefer to use the early voltage over current, or if that's still comfortable to you at this stage, it's really early voltage over current. And so you get all three of those terms in a very direct way. In a both threshold, by the way, it's very similar. You notice a similar behavior on these, except that instead of UT, I get the sort of term which is sort of overdrive over 2, effectively. And that's really what is the kappa times gate voltage minus source voltage minus, basically kappa minus gate voltage minus threshold, and then threshold after it, or then source voltage after it. And that's really important because it means that where I'm biasing will determine a number of parameters above threshold. So the above threshold dynamics is actually a bit more complicated, though sometimes we'll need it because just the performance of the circuit we're doing is going to require it for one reason or another. Higher speeds, or usually higher speeds, but there's a few other cases that you can see it. So these are the things we'd look at. So these are your three terms, and you would just define them and go, okay, that's great. Now, interesting question, of course, is, obviously I is my bias current. So remember, there's a bias current in the circuit, often determined by the fact that I put a current source somewhere, right? Everything is really based around current source type of techniques. So it's usually pretty easy to figure out what the bias current is because I've usually set it somewhere, or it's some combination or difference of current sources. The other thing is people will typically ask, oh, well, okay, what are the parameters of kappa and sigma? And what you'll typically find is that kappa, goes about 0.6 to 0.8 for a lot of devices. It can shift a bit out of that, but it makes sense. Sigma typically is in a nice wide range, which corresponds to early voltage of 100 to like 10,000 volts. I mean, you see numbers like this, you will see stuff out of this range as well. But it gives you an idea of what we're seeing as we look at this. But we'd kind of miss something if I didn't. If I just look at it, it'd be just a set of equations. But what I think is important is to understand a lot of the key products you see of these, because effectively you rarely ever see one all by itself. And so, for example, if I look at sourced, if I were to say something like a common drain volt, right, which would then cut this one off to 0, I would just get the GM and the GS term, and that ratio is what is important. Well, the ratio of GM to GS is kappa. Not surprising. This is, of course, the coupling I would get from basically, the difference in coupling that I would get in terms of the gate side to the source side. No surprise there. And if I set up a feedback structure, that's what I'm going to see. Same above threshold. GMR0 is actually what happens in terms of the gate and resistance. This is very typical. If I had a common source amplifier, I just get these two terms. And that product then turns to give me kappa over sigma. Which is, if you remember from a common source amplifier, is exactly what you get from the large signal analysis, which is really good. And you'll see this term almost always being used again and again. And again, I get the third case of GS R0, which is then 1 over sigma. This is actually also a really important comment for source driven amplifiers, but also for things like cascodes and other circuits of this sort. So, particularly in subthreshold. Now, above threshold, you have to know where your overdrive voltage is. You have a number of things to calculate there to get it right, but it's still very doable. In subthreshold, there isn't usually much to calculate. You pretty much know kappa, you know sigma, you can kind of ratio kappa over sigma. You could know sigma. There isn't much to calculate ever. And this is actually what's beautiful about the analysis, is that I can now talk about really talking about what's the concepts and the intuition of the circuits, rather than saying let's actually derive math for 20 problems. And this is something that should be kind of understood and in some sense hopefully appreciated as we continue through and the enabling of being able to do more and more complex and interesting circuits.